It's the year 2050, and our global megacities are suffocating. A dense, toxic yellow smog has blanketed the skyline, turning metropolises into absolute dead zones. Looking at heavily polluted urban centers today gives us a very real preview of this crisis. In the Synapse city scenario, these environments have degraded to the point where they are extreme danger zones. Sending a human being inside is completely out of the question. That brings us to Project Atmos. The objective is a large-scale deployment of autonomous robotic defense systems designed to physically scrub those pollutants out of the air and restore the biosphere. We cannot solve this by engineering better hazard suits for people. The only viable path forward is to remove humans from the rescue equation entirely. To pull this off, we have to move past traditional robotics. Historically, we relied on a code-to-run framework, where machines execute static, predefined instructions without any awareness of what's actually happening around them. When you send a rigidly programmed machine into a dynamic hazard zone, it fails. The moment it encounters an unexpected barrier, it crashes and spins its wheels, blind to the new reality of its environment. Here, we see the strategic timeline of the AI IoT Robot Challenge, or AIROC. This shows the shift where the heritage of standard robotics transitions into a code-to-think framework. This requires a new discipline called physical AI, which is built on 3 pillars. First, the robot must see using computer vision to identify objects. Second, it must think by running algorithms to map its own path. And third, it has to communicate with other machines using IoT protocols. This approach creates independent ecological first responders, capable of evaluating their own environments without human telemetry. The 2026 AIROC event acts as a high-stakes training ground to prepare students for this exact 2050 crisis scenario. This diagram shows the Synapse grid, the official competition battlefield. It's a strict 4x4-foot physical track divided into 8 distinct city sectors, marked by blue diamonds, along with a green terminal zone. Looking at the hardware specs for the Leanbot system, you'll see exactly how these machines survive the grid. They use ultrasonic sensors to measure distance, alongside specialized color tracking sensors and an IoT connectivity module. This graphic breaks down Mission 1, Containment, which tests the see capability. The robot must visually detect a solid-colored pollution block and physically push it until it overlaps that blue boundary line. Mission 2 tests the Communicate pillar. Notice the dotted trajectory line here. Advanced fleets use their network connection to coordinate and deliver striped neutralizer units from the storage area to the specific pollution zones they match. Finally, we see Mission 3, Analysis. Look at the mystery block icon and the green crosshairs targeting the terminal. Master-level robots must utilize search algorithms to locate an unknown block and autonomously transport it back to base. Navigating the Synapse grid requires dynamic machine intelligence to solve a spatial puzzle that changes in real time. But assembling the physical robot and understanding the grid is only half the battle. The actual operational procedure introduces a massive logistical hurdle. Here we see the cyber-physical bridge. Before a student ever touches the physical hardware, they must build and simulate their pathfinding algorithms inside a digital twin, a perfect 3D virtual mirror of the real-world track. Look at Stage 3, Quarantine, on this flowchart. Robots are impounded and software code is permanently frozen. In Stage 4, actual pollution colors and locations are hidden until the start. Real-time variables are only revealed after the code is locked. By freezing the code before revealing the crisis variables, the competition proves whether a robot was merely programmed to execute a script, or if it was truly programmed to think and adapt. Everything culminates in a high-pressure, 2-minute physical run on the grid. During these 120 seconds, 0 human intervention is permitted. The pristine digital strategy must physically clash with the unpredictable friction of the real world. If teams tie on points, the winner is chosen by sheer algorithmic speed and the round-to-round consistency of the machine's decision-making. Inside this 120-second crucible, human intervention is physically impossible. Success depends entirely on the resilience and autonomy of the programmed logic. Stepping back from that 4x4 grid, you start to see the real-world scale of the AIROC initiative. Looking at the Global Alliance history, we can see how much this has grown since 2006. It now connects a vast network of young engineers across Indonesia, Malaysia, the Philippines, Vietnam, Thailand, and China. While the toxic smog of Synapse City is currently a speculative simulation, the environmental threats we face outside those doors are rapidly becoming our reality. By mastering physical AI, these students are writing the foundational logic for the autonomous systems that will eventually restore the biosphere.